All right, here we are in section 4.2. In the previous section, I defined congruence for you. We talked about the symbol for congruence. We talked about so-called CP/CPE, corresponding parts of congruent polygons are equal, which is really just what congruence is. And then here in section 4.2, I will drop, well, actually not quite drop, but lead you up to the congruence postulate for the chapter, so-called SAS Triangle Congruence. We will find that this is a shortcut to congruence. It'll be an easier way, a way that requires less information to prove that in particular triangles are congruent. So let's get started. So here's what we know from the previous section. We know that congruence is actually 6 total equations for triangles, of course. It would be 8 for quadrilaterals and so on. For instance, when we say that two triangles are congruent to one another, we mean that each side of one is equal to a side of the other, and each angle of one is equal to an angle of the other. And that is 6 total equations, which is quite a bit of information. So if you're told, for instance, that two triangles are congruent to one another, that immediately becomes 6 equations. 3 about sides, 3 about angles. Now, what we will find in this section and in later sections as well is that shortcuts to congruence exist. That is, you are able to prove that triangles are congruent with less than 6 equations. The shortcut to congruence that we will discuss today is so-called side-angle-side congruence, and this will be a postulate for us. That is, it will be one of our basic assumptions. And all the other triangle congruence principles or shortcuts, and there will be 4 more after SAS, as side-angle-side, all of those will be proven, and those proofs will commence in a couple of sections, that is, in section 4 of the chapter. But here we have the postulate. In the next section, we will make use of this postulate to prove an extraordinarily important theorem that is called the isosceles triangle theorem, which I believe I have mentioned before. So my intent is not to simply drop the postulate on you and say, accept it, but rather to lead you to the postulate with what I call an intuition pump. That is, I'll show you a sequence of diagrams to pump up your intuition, and by the time we are done, I believe you will assent to the side-angle-side triangle congruence postulate. Indeed, I think you will find it quite obviously true, which is a feature that postulates should have. I mean, Euclid surely thought that this was true of postulates, that postulates were not merely basic assumptions. They are that, of course. But in addition to that status as basic assumption, they are simply quite obviously true. Okay, so here we go. So step 1. Let's begin with an angle. Okay, so that angle has vertex A. And I've added something else into the diagram that shows its angle A, and that is the symbol alpha. That's the symbol that you see tucked into its interior. Now, what this alpha represents is the measure of the angle. And what I wish you to understand is that this particular angle doesn't have like a variable measure. Instead, its measure is fixed, okay, whatever it happens to be, like 30 degrees, 45 degrees, whatever it is, doesn't particularly matter, but it is fixed, okay? And that particular measure at which this angle is fixed is called alpha. Okay, now step 2. Here's what we do next. Okay, so we leave the angle measure alone, and what we do is this, is we go out a certain distance on each side of the angle and drop in a pair of points, okay? And we will call them, oops, I didn't get this quite right. We will call them B and C. Sorry about that. This is what happens when you edit, but forget to go back and make all the necessary changes. So what then follows is that these lengths AB and AC are fixed, just as the angle measure itself is fixed. So again, on each of the sides, drop a point at a particular location. That must be emphasized, okay? So one of those is B and the other is C. And then what that means is this, is that we end up with particular lengths, AB and AC. Now, step 3. Step 3, let us connect points B and C to produce segment BC. And of course, we end up with a triangle here, triangle ABC. And the dashes for segment BC have no geometrical significance. I simply did this to make them stand out. Okay, so we end up with triangle ABC. Now, I have a question for you about this particular triangle ABC. Remember, everything is fixed, right? We're not everything yet, we know. But instead, the angle and the distance out the sides, those are fixed. So let me ask you, is that final side length also now fixed? And how about the other angle measures? Perhaps we can go back and look at this. Is the length BC fixed? given that AB is fixed and AC is fixed and alpha is fixed. How about the measure of angle B? Is that fixed? How about the measure of angle C? Or here's another way to ask my question. Could those change? Could we keep alpha, AB, and AC precisely the same as they are, and yet still have variation in BC, or variation in the measure of B, or variation in the measure of C? And the answer to me seems quite obviously no. If I have fixed alpha, if I have fixed AB and AC, then BC is thereby also fixed. It is what it is and cannot change. And so too for the measure of angle B and the measure of angle C. So there's a consequence of this, okay? And it concerns pairs of triangles, which gets us very close to the postulate for the chapter. So let's say that what we did to produce that triangle ABC, we do it again. To produce the triangle A prime, B prime, C prime. Okay, and that's how you read that little dash symbol. It's not actually an apostrophe or a quotation mark. In this context, it is called a prime, and mathematicians very often use that prime to show associations between quantities or between objects. So again, what we've done is this: we've followed that same procedure to produce triangle ABC on the left-hand side, the one that I described before, and then we repeat it, and then we do it again, okay, to produce triangle A prime, B prime, C prime, okay. So we have the same measure for alpha, okay. The length of AB is the length of A prime, B prime, and the length of AC is the length of A prime, C prime, okay. So just did it again, exactly the same as before. Now, we agreed before that BC had to be fixed, okay. That is, it couldn't have some range of possible values, right? It had to be one particular value. Well, if we do it again, we'll have to get that same value again, which means that the length of BC will have to end up the same as the length of B prime C prime. And likewise, the measure of angle B, whatever that was, the measure of angle B prime will have to be the same. And likewise, the measure of C will have to equal the measure of C prime. Okay. Now, think for a moment about what this means. And I'll come back in just a moment and sort of officially state the postulate here. And we're really at the postulate now. Notice what this means. It means that if we have two triangles and we fix an angle measure, and we fix the sides that include that angle measure, that is the sides that come together to make that angle, then everything is fixed, okay? And if everything is fixed, then the triangles are congruent, okay? Then the triangles are congruent. And this really is the side angle side triangle congruence postulate. Okay, so let's go ahead and state it officially. And here's what it is. If two sides in the included angle, that is the angle they make, of one triangle equal two sides in the included angle of a second triangle, then those triangles are congruent. And this is called side angle side triangle congruence. So let us have a picture, a bit different than the one we had before. So I've got here a triangle ABC and a triangle RST. Oh, and notice that I have an angle of one equal to an angle of the other. Oh, and I have a side AB of one equal to the side RS of the other. And then finally, side BC of one is equal to side ST of the other. This is the side angle side pattern. I have two sides in the included angle of one triangle equal to two sides in the included angle of a second triangle. And what we then say in this case is that the triangles are congruent, okay? And do let me emphasize, okay, something that was implicit in what has been said. The angles that are equal must be included in between the sides that are equal. Okay, so notice the structure of this, right? The congruence postulate is called SAS, and that indicates that the equal angles must be in between the equal sides, right? So if, for instance, in my diagram, we were to know instead that angle A was equal to angle T, okay? I didn't know that angle B was equal to angle S, but we did know the sides marked are equal. Well, that's not side angle side anymore, okay? Because then the equal angles would not be in between the equal sides, okay? So you must look for precisely this pattern in the triangles that you have, and only then does SAS apply, okay? So notice this about SAS. Okay, so a really good question is, what does the postulate do for us? I mean, that's always important. Postulates are supposed to be like, engines. They're supposed to get us someplace. Well, here's what SAS does for us. It increases information about a pair of triangles. We begin with three equalities, two sides equal to two sides, and an angle equal to an angle. And then we get three more, okay? We will know once we have concluded that the triangles are congruent that the other pair of sides are equal and that the other two pairs of angles are equal as well. Okay, so let's go back to this diagram with ABC and RST. If we have the equalities that are marked in the diagram, then it follows by SAS congruence that the triangles are congruent. And then it follows by here's the rule, CPCTE, that also AC is equal to RT, that the measure of angle A is equal to the measure of angle R, and the measure of angle C is equal to the measure of angle T. Okay, these follow. So what SAS congruence gets us is 3 equations that we did not have before. So it introduces quite a bit of new information, and we'll find that extremely helpful when we put together our proofs. Indeed, this is one of the fundamental postulates of the entire class, the entire mathematical system that we will put together. It does so much work for us. All right, so let's talk about SAS congruence proofs. Okay, so let's actually begin to put SAS to work. So the basic strategy here is this. And congruence proof is one of the basic kinds of proofs that we do in this class. Typically, what we do with triangles, if we ever have more than one triangle in this class, is we prove them congruent. So let's begin to talk about that. Okay, so how do we do it? Well, we need to prove, if necessary, if we don't already know it, that 2 sides and the included angle of one equal 2 sides and the included angle of the other. Then once that has been done, we will be able to conclude that the triangles are congruent by SAS congruence. And then, if necessary, we will use CPCTE to infer that a pair of sides or angles which correspond are equal. Okay, so let's actually do some examples. And I will go through these fairly slowly because I want you to have a really good sense of how it is that we do congruent proofs. Okay, so look at the diagram. Apparently we do have 2 triangles. And remember what I allow you to assume unless I tell you explicitly otherwise, that what looks straight is straight. So the path from A to M to D, since it looks straight, we will say that it is. And likewise, the path from B to M to C is straight. Okay, so we're told about this diagram that AM is equal to CM. And I absolutely recommend that if the congruence symbols, the hash marks, if they don't appear in the diagram, go ahead and draw them in, okay? At least what appears in the given. So AM is equal to CM, and BM is equal to DM. And we have no reason to suppose, of course, that all 4 of those are equal, so let us use 2 hash marks the second time. And then what we wish to prove is that triangle AMB is congruent to triangle CMD. Okay, so let's actually think about this before we get in, before we begin the proof. Well, the assumption here, of course, is that we will make use of SAS congruence. Well, we don't have enough information to use it yet. We don't have enough information in the given, that is, because all we know is that 2 sides of one triangle are equal to 2 sides of the other. We do not know that the included angles are equal. That is, we do not know that angle AMB is equal to angle CMD, and we need to know that to make use of SAS congruence. So let me ask, do we know something that would allow us to conclude that those 2 angles are equal? And the answer is yes, of course we do. As I reminded you a moment ago, what looks straight is straight. So those angles AMB and CMD are vertical. And then by the vertical angles theorem, we may conclude that they are equal in measure. And once we have done that, then we will be able to apply SAS congruence and conclude that the triangles are congruent. Okay, so we'll have statements. They will come from something, by something. I believe that I'll begin to use these abbreviations, S and F and B, for statement, from, and by. And then, of course, we start with a given, which, once again, we've already stated it, so we don't need to state it again. Oh, and then what else did we need to prove congruence? Well, we needed that angles are equal. So let us say that the measure of angle AMB is equal to the measure of angle CMD. Okay, and don't say that the measure of angle M is equal to the measure of angle M, okay? Because I will have to figure out what you mean by the first M and by the second M, okay? Use the full 3 letters name so it's clear which 2 angles you mean here. Okay, so that follows from the given, because the given, tells us that we have vertical angles. It does insofar as it gives us 2 lines that intersect. And then that follows by the VAT, okay? And then notice what we then have. We have 2 sides in the included angle of one triangle equal to 2 sides in the included angle of a second triangle. So it now follows that the 2 triangles are congruent. And we will say that they are. And of course, let me emphasize again that we pay very close attention to the order of the letters in the congruent statement. So AMB is congruent to triangle CMD. And that gets it right, doesn't it? Because angle A is equal to angle C. First equals first. Angle M equals angle M. Of course, AMB and CMB. And then angle B is equal to angle D. Yep. And it also gets the segments right. So those are definitely the proper order of letters. Okay, so let's see. From what did this follow? Well, it followed by SAS congruence. Okay. And where was the information necessary to apply SAS congruence? Well, part of it was in the given for sure, because we needed those two pairs of equal sides. And the other part, the pair of equal angles, is included in line number 2. So SAS congruence, in this case, needs multiple previous lines, and that's very typical. Usually SAS congruence does, and the other congruence principles that we will see later on. Okay, and with that, the proof is complete. All right, let's do another one. So, take a look at the diagram. Take a moment to digest it. We have an angle ABC, and then we have this segment BM that cuts angle ABC up into 2 parts. Oh, and then we're told in the given that BM actually bisects ABC. And remember that bisects means in particular that the 2 parts are equal. Okay, so we'll go ahead and mark that. That's information that's in the given. Oh, and we're also told that AB is equal to AC. Oh, and then we wish to prove that the measure of angle A is equal to the measure of angle C. So I'll just simply draw arrows at them to focus our minds on what we need to do. We need to prove that the measure of A is equal to the measure of C. Well, I mean, how possibly could this happen? The answer is this, and this will almost always be the answer in this class. We will prove triangles congruent, and then we will use CPCTE. Okay, so let me emphasize that. Let's say that at some point in this class, you have a pair of triangles, and you wish to prove in them that a pair of angles or a pair of sides are congruent. Here is almost always the way that that gets done. You will first prove that the triangles are congruent, and then you will use CPCTE to prove that that pair of sides or that pair of angles are indeed equal. Okay, that's just how this goes. It's one of the most common proof patterns in this class. All right, so let's think then about how we will prove the two triangles ABM and CBM congruent to one another. Oh, well, I have AB in one equal to CB in the other. I have angle ABM in one equal to angle CBM in the other, and then notice something very curious. I'll mark the diagram like this. BM is part of both, okay? BM is part of both. And of course, BM as part of one is equal to BM as part of the other. Of course, right? I mean, it's part of both, so it's one in the same segment, so it's the same in both. And then, of course, the question is this: how will we actually write that in the proof? Well, we will write it as BM is equal to BM. And that is interpreted in this context to mean that BM as part of triangle ABM is equal to BM as part of triangle CBM. And do you happen to recall what that rule is called when we say that a quantity is equal to itself? In this case, that BM is equal to BM. That's reflexivity. So here it is. Reflexivity is actually useful. So statement and from and by. And we have the given, of course. And then what did we need to say to prove triangles congruent? That BM is equal to BM. Yeah, and that follows from the given, because the given gives us that segment. It tells us it exists. And that is by reflexivity. Okay, and then notice at this point that we do have 2 sides, and the included angle of one triangle equal to 2 sides of the included angle of a second triangle. So we can say that they are congruent. So we can say that triangle ABM is concurrent to triangle CBM. And I think it would be worth your time to pause for a moment and to verify that that order of letters is correct. Okay, so that follows by SAS congruence. And what do we need to do that? Oh. I tell you what, I'll pretend once again that I actually intended to do this. But notice something that we didn't do. We never actually said that an angle was equal to an angle. Okay, it is true, of course, that an angle is equal to an angle, but we never explicitly said it. And the reason that we know that an angle is equal to an angle is that we're told that we have a bisector. Okay, so let's explicitly state that an angle is equal to an angle. So we know that the measure of angle ABM is equal to the measure of angle CBM, and that comes from the given by the definition of bisects. Okay. And now we have explicitly been told that 2 sides and the included angle of one triangle are equal to 2 sides and the included angle of a second triangle. So it now follows that triangle ABM is congruent to triangle CBM. And let's see, where is the information for that? Well, part of it's in the given. because the given says that AB is equal to AC. Part is on line number 2, where we have another pair of equal sides, which is really one side twice. And then on line number 3, we have the included angles equal. So actually, this is the first instance where we've had to make reference to 3 previous lines. And then how do we get then that the measure of angle A is equal to the measure of angle C? Well, those are angles that correspond in triangles that we now know are congruent. So it follows that the measure of angle A is equal to the measure of angle C from 4 by C, B, C, D, E. And with that, the proof is complete. And I'll go ahead and stop right there. There's one other slide, and all it says is this, is that, yes, reflexivity actually matters. It might seem like it's a ridiculous rule that, of course, every quantity is equal to itself, but how does that ever help us? Well, it helps us when we have a part of 2 triangles that is shared in common.